for the purpose of doing this, we're going to assume that wherever we say g of x, I'm referring to f inverse of x, because it's weird to write f inverse prime, so we're just going to write it as g. The first problem, the easy type, is given a function, you want to find the derivative of the inverse. So say g prime of 2. It's real easy. You just have to find the inverse and differentiate it. So you figure that out by switching x and y. X cube it. And then you pop out with y equals x cubed plus 1, which is really g of x, the inverse. Differentiate and plug in, and that's it. G prime of x, 3x squared. And then evaluate it when x is 2. Equals 2, and you get 12. And away we go. But that was easy. For the more difficult ones, well, something happened. You posed the same question, but when you're given f, you say, okay, find g prime of 3. Your first instinct is to find what g is, so you switch up x and y. You get the old x plus y cubed plus y plus 1. And you run into this problem, because you can't isolate y. You think, well, does it even have an inverse? What's going on? Regardless of the fact that we can't isolate y, just by virtue of the fact that we switched variables means that y is now the inverse of the thing that we started with. So we can still differentiate it, we just have to do so implicitly. So when you switch it up, these are really g's. We can differentiate this with respect to x, giving you 1 y squared, and we can isolate y prime. Y prime equals g equals 1 over 3y squared plus 1. See, it's kind of a problem because we want g prime of 3. Oh, I'm sorry, g prime. We want g prime of 3, but the inverse, the derivative of the inverse, g prime, is given in terms of the y coordinate. So we can't plug in 3 here. What this y value is, it's the y value that corresponds to x being 3 on g inverse. I'll give you an example. If you look at, let's say that we knew what the graph of g was. Let's say that this is g of x. And in essence, we are looking for the derivative at 3. We want the slope of the line tangent to the graph of g when x equals 3. But it's given in terms of the y coordinate. So let's say that, just for hypothetically speaking, let's say that we knew that this point was 3, 4, say. Let's just assume that. If we knew that, then to evaluate g prime of 3 when x is 3, all that we would need to do would be to plug 4 into here, and we would be finished. But we don't have. But that's what this means. That's what you have to try and find. You need the y value corresponding to x equaling 3. But it's not 4. We really don't know that. So, but you know that there is some point there. So what we're going to do is we're going to say, okay, there's a point on G, 3, B. We don't know what B is. B is the unknown. Well, so if on G there's 3, B, and G is the inverse of F, then on F, so on the graph of F of X, there must be the point B, 3. And that's the method by which we find B. Since you know that B, 3 is a point on F, you know that F of B must equal 3. And so you run it through the function F of B is, going back to the original, B cubed plus B plus 1 equals 3. The solution of this equation will be the value of B that we're looking for, and that's going to be the value of Y we're going to plug into the derivative. Since I didn't want to make this an exercise in solving algebraic equations, you could just kind of eyeball this up and say, okay, by inspection, the solution is B is 1. B is 1, you plug in 1, you get 1 plus 1 plus 1 is 3. That's the value of y that we're looking for. We got it. So that means that on f of x, there's the point 1, 3. Which means that on g, there's the point 3, 1. And hence, to figure out what the slope of the line tangent to g is when x is 3, the corresponding y value is 1, you just have to plug in y equals 1 for this, and you get 1/4. And that's the end of that.